My name is Jeff Keaton. I'm with AMEC Foster Wheeler and a member of the GEER steering committee. I'm accompanied by Scott Anderson with BGC Engineering. He's in Goldon, Colorado, and also a member of the GEER steering committee, and Joe Gartner, who is also with BGC Engineering and in Vancouver, British Columbia. This webinar is something that the GEER steering committee talked about for a long time last year and made the decision that we would do it. It got a little close to Christmas and we pushed it off to this year instead of doing it last fall. But post-wildfire sediment discharge and infrastructure impact is in the news these days, and as you all know, and you'll see some information about what happened 1 week ago today in Montecito on our presentation. So let me tell you a little bit about GEER. It stands for Geotechnical Extreme Event Reconnaissance Association. It is supported by the National Science Foundation and organizes members of the geotechnical community to respond to selected natural disasters. We have a discussion about the merit that would be available for certain disasters when they come to our attention, and we mobilize a team. Our objective is to collect information that will help understand the engineering aspects, primarily with infrastructure impact, particularly those elements that tend to be obliterated by weather or cleanup rapidly and therefore don't last very long, but may be very helpful to understand process. Our National Science Foundation support is in the form of expense reimbursement. GEER members donate their time, capabilities, and resources while they're working on the missions, the reconnaissance missions, and generate reports really rapidly. We try to do them within 2 or 3 weeks of the time we're in the field, and all of them are posted on the GEER Association website with the link at the bottom of all of the slides. This is what the GEER Association website landing page looks like, a map of the world with icons that represent reports of different type. Our outline today is an introduction that's in progress. Joe Gartner will take over with sources of information about burns. I'll come back and talk about weather radar and its value for a bulk of the time. And then Scott Anderson will talk about the impact to infrastructure and what the social media opportunities bring to us to enhance and support our reconnaissance missions. So here's a zoom on the US part of the landing page of the GEER Association website. The 3 icons that have the year listed beside them were flood events that included sediment discharge from burn slopes. So we do have some experience with that. This is a diagram from wildfires of the US or in the US. It's the 2017 page at the end of last year. So you can see the yellow item there in Southern California is the one that was within the last 7 days. So this was at the end of December while that fire was still burning. And if you look at these two, the wine country fire known as the Nuns Fire in Northern California damaged or destroyed nearly 9,000 structures and caused 43 fatalities. The Thomas Fire, which is in Ventura and Santa Barbara counties here in Southern California, damaged or destroyed over 1,100 structures and caused 1 fatality in the fire. Multiple other fatalities have resulted from the post-fire sediment discharge event last Tuesday, which is really sad. This is Sunday, an announcement on the National Weather Service from last Sunday, or not last Sunday, but the Sunday before the flooding event occurred, and it was a watch because it was still 2 days away. But it did forecast rainfall rates in excess of 1/2 to 1 inch per hour as an intensity value. And it gives time in the year, month, day, and then time in the Universal Time Coordinated, UTC, which has got the designation of Z for Zulu, and the location of Montecito is underlined there, and it says it's in effect from 4 p.m. Monday to Tuesday evening. which corresponds to the times that are underlined near the top, which are in the UTC format. And it also identifies burn names, including the Thomas burn. And so with that, Joe, if you would request to take over here, please proceed.
Okay, thank you very much, Jeff, for the introduction. So when you get to a burned area, it can be pretty overwhelming with, can be difficult to get your bearings. You might be inundated with information. There's, particularly in Southern California, there's multiple jurisdictions that are all providing some level of detail at the federal, state, county, municipal, and city, or like engineering, flood control districts. They're all giving information. So it can be difficult to sift through to get relevant information that's helpful for your purpose. But fortunately, the recipe for a post-fire debris flow event is quite simple. All you need is a fire, particularly moderate to severe fire, steep slopes, and intense rainfall, and then you'll get mud or debris and trees or what else. As you can see this photo from Southern California, you have this situation frequently. And this situation abuts right up against homes and infrastructure in a pretty dense urban area. So that's where we get the problems. So let's see, trying to advance the slide here. Here we go. Okay, so just a general outline of this portion of the presentation. I'll talk about some good sites and resources for getting general information about the fire, some more specific detail for burn severity, fuels, that can provide you more detailed information for where the high and moderate severe fires, or high and moderate portion of the fire happened. And then I'll go into USGS hazard assessments and how you can use those hazard assessments to identify where your sources of sediment are and where they may run out downstream. So a really good website for getting general information for the fire is this Inciweb website, and it gives all kinds of related links and general information about the fire, including how big the fire is, if it's been contained, how it was ignited. They'll give daily updates and recent articles, and also it's not shown here, but there's also Twitter links and all the links to the various players that are involved in fighting the fire and dealing with the fire cleanup. Really helpful link that you might find here is a link to the BAER report. BAER stands for Burned Area Emergency Rehabilitation. And what this is it's an interdisciplinary group of Forest Service, USGS, and university professors and other professionals related to wildland fire that get together, essentially lock themselves in a room and do a rapid assessment of the fire and the fuels that led to the fire, and also identify where sources of sediment may be problematic and how to allocate potential funds towards stabilizing slopes using log erosion barriers or straw mulch or aerial seeding. Moving on, another helpful website to help you get your bearings is the geomag.gov website. This screenshot is, it's kind of out of fire season, but you can see these little green triangles, and this is a fire, and you can zoom in to each of these fires and see the perimeter of the fire. You have capability to download fire perimeter and also to view past fire perimeters. So this is a zoomed in view of here's the recent Thomas fire. You zoom in, you can see the burn perimeter, so you get a general idea of where this thing is located. And you can also navigate to see, well, what other fires have happened in the area. Now, in the recipe for post-fire erosion I showed earlier calls for areas of high and moderate severity fire. And these burn perimeters don't provide you with that level of detail. So to get that information, you would go, well, let's just talk about burn severity. What is burn severity? Shortly, it's the change in the soil and forest caused by the fire. So the fire, So burn severity layer is a measure in the change in vegetation caused by the fire. And it's a proxy for identifying the temperature intensity that the fire burned out. So when the vegetation is removed, you can get dry raveling of sediment that was previously anchored by vegetation. Rain's able to fall directly on the hill slopes, and runoff is less impeded by organic woody debris, litter, and duff. Higher intense burn severity or burn temperatures can create water repellent soils, which decrease the infiltration capacity of rain falling on the soil surface. And these changes to the vegetation and soil change the hydrology of a catchment or watershed. And this is why burned areas are more susceptible to erosion than unburned areas. So I like this photo because it shows a really kind of distinct pattern of low severity burn in these where the canopy hasn't been burned, and then these high severity streaks. So just keep an eye on that pattern. And this is the related burn severity map for this area. And this is a fire in British Columbia from 2017. You can see these same patterns of high and low and moderate severe burn. So with this map, you may be drawn to these red areas and think, okay, well, the high severity fire, that's where we're going to get the most erosion. But you also need steep slopes. And so this map demonstrates how you can see the contour interval up here in the high severity areas pretty far apart. So these areas are pretty flat, although they're burned at high severity. So the takeaway here is that you may find that these steeper areas that are burned at moderate severity are where your sediment is eroding from in a burned area. So the Earth Resource Observation Science website, EROS, is the link that is very helpful for getting the burn severity data for recent fires and also for historical fires. There's also links to get information for soils, vegetation, and wildfire outlook, fire danger. I'm going to focus on these links outlined in red here. So the first one is for, this is the Monitoring Trends in Burn Severity website, or MTBS. And this is where you can find all burn severity data for fires from 1982 to present. This website is updated periodically. I think the last update was 2016. So it may not have the fire that you're interested in if it's within the last year or so. However, this is a really good website for understanding the history of fire in an area. So you may come across someone who says, well, we had this fire in the 90s and nothing happened. So why are we getting a huge debris flow event from this fire? And you might look back to that previous fire and see that it burned mostly at low severity, or was patchy and didn't really affect the steep parts of the watersheds. So this is what the burn severity data looks like. The burn severity maps are created using an algorithm that compares pre and post fire Landsat imagery. And it comes up with, and the term for this is called the BARC map. It's the algorithm produces a map with 256 bands, and then based on ground reconnaissance, they adjust the distinction where those they reclassify those bands into low, moderate, and high severity. Most of the data you'll get is already been reclassified, but sometimes you'll get a raw data file that has 256 bands. So you might have to look into where the best breaks for those are. There are standard breaks that are associated with these, and that all that information is on the website on how to figure out where the low, moderate, high severity breaks are. So for more recent fires, the Forest Service BAER support website provides a good link. During the fire season, this website is updated weekly, and so this you might be able to find your fire severity data here. However, for the recent Thomas fire that in near Ventura and Santa Barbara County, where the devastating debris flows occurred last week, that information has not been, the burn severity data has not been released yet. And the reason for that is typically the burn severity data isn't released until after the BAER team, the burned area emergency reconnaissance team, issued their report and had the time to calibrate the burn severity to reflect the actual conditions in the field. So the last website I'm going to talk about is how this data is used by the USGS to provide rapid assessments of debris flow probability or likelihood and magnitude or volume, debris flow volume. The landslides group based out of Goldon has put together this wonderful viewer. They're really cranking out these assessments for the burned areas. And this is the landing page for their viewer, and you can hover over and click on one of these fire icons. The Thomas fire down here, I think, is this one here. And if you click on it, you'll be brought to a page showing a number of maps, and you can select what data you're looking at by this little layers icon up here. 3 types of maps are provided. There's a debris flow likelihood, debris flow magnitude, which is expressed as the total volume of debris flow material. And then these, they're broken into these classes, and those breaks are reclassified and added together to come up with a combined relative hazard map. So you can distinguish areas that have like a high probability and a high volume is going to have a high hazard versus somewhere with possibly a low probability and a high volume might have a moderate hazard, as you can see here. So it helps to distinguish the areas that are various probabilities, magnitudes, and how those interact. Because if you have somewhere that's got a real low probability, but it's a high volume, it might not be as much of a threat as somewhere that's a really high probability area, but low volume. So these data, the way that these models work is a pour point signified by these black dots is used to delineate a basin, and the model looks at the distribution of the area burned at low, moderate, and high severity, rainfall intensity, soils data, terrain morphology, to get an idea, to get an estimate of the conditions at that pour point. So that's fairly, and then the watershed is color coded based on the information at the pour point. So it gives a good visual representation of where the material is coming from. But it also doesn't necessarily give you an idea of where material might flow. So this is from our where the debris flows last week were in Montecito. And these are the communities that were affected downslope of these debris basins. So to account for that, the models are also applied for stream segments, so that every portion, every point along the stream, there's a hazard assessment estimate made along the creek. And then downstream, since these models are most applicable to the area upstream of a drainage outlet, these blue lines downstream signify areas where you could expect high sediment yields from maybe debris flow deposition or debris flood discharge or high water flow, maybe trees floating down. So this gives you a more complete picture of where within the burned area you might have the most erosion from debris flows along the channels here, and also the paths that those debris flows may travel out and transition into debris floods and floods downslope. And this is really useful information for communities. This is a photo from the station fire, which is in the San Gabriel Mountains. But this is looking down from the top of a watershed and looking downstream, and you got a dense urban area down here. This area has a debris basin at the base of it that filled up, but had that not been there, it may have flown out, and you may have had a similar situation as we had in Montecito last week. So with that, that's all I have for this portion of the webinar, and I'll pass it on to Jeff to talk about rainfall.
Okay, thank you very much, Joe. Appreciate that. What I'd like to do now is give an introduction to NEXRAD Doppler weather radar and what the color designations and the scale that's used for that depiction is. Then I'll show something about how just a graphical representation can be quite useful, and it's easy to get that. And then go into a little bit on how we do the quantitative assessments, which is also quite interesting and valuable. The WSR, excuse me, 88 is weather surveillance radar Doppler developed in 1988 or deployed in 1988. The array of stations is shown there with the map and the blue dots. There's a unique scale. It's like an acoustic scale. It's called decibels in the Z scale. It's high energy microwave or radar pulse. It's about 400 times more power than what you have in the microwave in your kitchen at 450 kilowatts per pulse. The pulse of energy lasts for about 1.5 microseconds, and the remainder of a millisecond is used for listening to the returns. So the whole pulse series is 1 millisecond at a time. It amounts to about 7 seconds per hour of energy output and 59 and a fraction of minutes per hour of listening and data collection. Base and composite reflectivity are commonly available. You see these on the NOAA, the Weather Service radar utility online or on your smartphone, and the one that comes up by default is base, and that's the lowest half-degree view closest to the ground, so that's capturing the moisture that's in the atmosphere real close to hitting the ground. The composite includes the upward-looking scans of the radar and gives the potential for precipitation that has yet to reach the ground. It has two modes, a clear air and a precipitation mode. The clear air is scanning when weather doesn't really demand very much data collection or doesn't warrant it. And so it's 5 elevation scans in a series about 10 minutes apart. But when it goes into a precipitation mode, it scans more elevations, more rotations, and goes faster. So it's a 5-minute scan for the ones that I've used. And you can see a little graphic there for what the elevation range is for the scan. It's a 1-degree beam, by the way, that is scanning out there. This is a view from the Climate and Weather Toolkit. The URL is down here. We have a collection of URLs that we'll show at the end of the presentation while the discussion is going on, so you can write these down at that time if you would like. And I'd also point out at this time something I didn't mention earlier, and that is we have a chat box. And so as you think of questions, feel free to put those into the chat box, and we'll use that as a method of the dialogue, the discussion. And this is being recorded, and that recording will be available with a link through the GEERassociation.org website. For anybody who has that link or goes to find that link will be able to see this. So we have a toolkit here that is this is the viewer in it after I selected a scene to deploy. This is the clear air. It is giving me what the mode is here in code words and what the maximum intensity is in terms of dB and the Z scale. And what you see here is colors that stay the same, but the scale changes for clear air versus precipitation mode. For your information, this is up in Seattle. Seattle is down here somewhere. This is the radar station, and that happens to be the OSO landslide location. So this is something that we did on the OSO reconnaissance mission. And so here's what it looks like under the precipitation mode, and the warmer colors indicate higher intensity precipitation. And I'll give you more information about that right here. Refer to the jet stream reflectivity element on the weather station or the weather service website. So here's the decibels in the Z scale, the rain rate in inches per hour and in millimeters per hour. And because I do my calculations in a spreadsheet, I need to have a continuous function that will allow me to convert the reflectivity to something that I want to use in terms of intensity of rain. And so here's the equation that I determined from these data over here, and the R squared and all of that stuff you can see there. But those kind of details are not what we really want to accomplish here. So if you search for the Weather and Climate Toolkit, it will take you to a page that has other links. Over here on the left, if you select radar, it takes you to a page with other links. The interactive map is where we want to go. So you click on that, and it takes you yet to another spot. And that's this one over here on the left that gives a list of the kinds of observations that you can view using that interactive map. We select radar, and then we have a controller unit here for radar, the type of product. We're going to focus on the level 3 because it has many more products, and many more than I will describe here, and an array of stations that you can zoom in on and understand where the data come from, but it's really a mosaic of radar data. So if we show the quality or the confidence that we have in the radar signal, the yellow over here is considered what's labeled here as better radar coverage. The best radar coverage is shown in green over here. I didn't show them in the same diagram, but you can stack these things to take a look at them if you want to do that. And the location of the radar stations is shown in the little dots, and the radar reflectivity scale bar is just displayed there also. So to give you a little bit of understanding of how this can be used in a value sense, here is the Thomas burn. This was an image that I collected just recently, but the burn was completed on the 27th of December, not very long ago. So I went into January 9, and I picked 8:45. I actually looked at different scenes and picked that one for display here. So Pacific Standard Time is UTC, that's Universal Time Coordinated, -8. So that means that's 45 minutes after midnight in the local area. And here's the weather off to the southwest over the Santa Barbara Channel. An hour later, that weather was seeming to become a little more organized, some higher intensity reflections down here. 2:45 in the morning, this band right here is the one that's going to do the damage, although it's raining real hard there now, preparing the ground for what is going to come in an hour or so later. At 3:45 in the morning, this area is starting to get the primary band that took about 20 minutes to move across, and that's where the bulk of the precipitation was that mobilized the sediment on those burned slopes and flushed it out into the neighborhood. So it's easy to understand, or it's possible to understand, and that's a really good tool for explaining some things. I'm not quite so sure at this point how to use it as a forward-looking tool with the level of confidence beyond what the Weather Service professionals are using for making their own warnings, which certainly have a lot of value. So let's look at the quantitative analysis, and this comes from the GEER reconnaissance mission that we did in December of 2014. I was the team leader on that one also. And it was the tropical moisture coming in pulses, 3 big storms in December of 2014. And this is the one that, this is when we decided we would try to do a reconnaissance mission. It was challenging because things were still happening around us as we were trying to get started. And to demonstrate the quantitative intensity and duration aspect, I'm going to use 2 fires in the east part of Orange County, the 91 Freeway Fire and Silverado Canyon Fire. And I'll make a brief comment about the Sepulveda Pass fire right here to make an important point. There's a little bit different view. The KSOX, or the Santa Ana radar station, is located right there on the Santa Ana Mountains. The 91 Freeway Fire is to the northwest, and the Silverado Canyon Fire is to the southeast, but very close to that station. And this is the location of the Sepulveda Pass fire, about midway between the Los Angeles radar station, KBTX, and the KSOX station, and I want to make a point about that as well. So here's a depiction from the viewer that we were just looking at. It shows the fair radar in blue, the better in yellow, and the best in green with the stations. I've got it listing only the level 3 data stations right now. And this comes from, this panel on the right comes from a USGS fact sheet from 2005 that shows similar information. It has real-time rain gauge locations, some of which I've not been able to find, many of which I have in terms of their availability for what I'm trying to do. So let's look now at the 91 Freeway and Silverado Canyon fires, which are located here in this depiction. A couple of rain gauge locations are here. Fremont Canyon and Temescal number 2 are the prime ones, or the commercial or the long-standing ones. The U.S. Geological Survey deployed a special purpose rain gauge within the burn of Silverado Canyon area, and that data was available to me also, and I appreciate the USGS for that. We had a storm on October 31st, the Halloween fire or storm that did cause debris flows from some areas in Ventura County. And then 3 storms in December, which are shown here in terms of the daily precipitation. And then the cumulative is shown in the blue line here, and that's cumulative for the month on a monthly basis. So I've circled in red the 91 Freeway fire location, the Silverado fire location down here. Unfortunately, I selected red as a color for the burn area. The 91 Freeway is too small to have a burn area. This one does have a burn area, but the red conflicts with the use of red color in the radar reflectivity, and I didn't think that through properly. So this is 39 minutes after midnight on the 17th of December in 2014. The storm is off to the southwest. It's moving. This is 10 minutes later. And 10 minutes after that, you can see a band has moved through, and additional precipitation is gathering, so to speak, in the Orange County Basin. And it's moving, it's getting close to the Fremont Canyon rain gauge, but it's remote, so to speak, from the Silverado Canyon fire. And the storm continues. This is now 1:29 Pacific time, and the main part of the storm is encroaching on the 91 Freeway burn. 10 minutes later and 5 minutes or so later, the heaviest part of the downpour is happening now, 1:49, and now this is 1:54. So it's almost 2 o'clock in the morning here. A very steep slope that had burned for the 91 Freeway burn and generated enough sediment to wash across all lanes of the eastbound traffic on the 91 Freeway, closing it at 2:15 in the morning. So that explains why we had sediment yield from this tiny fire that doesn't show up in many places because it was so small. This is what we can extract. These are the reflectivity values with the spiky things, radar rainfall, composite reflectivity, decibels in the Z scale, and the maximum was 55, and that's raining really hard. And then the cumulative for the Fremont gauge, and then the cumulative of my calculation using the radar rainfall and the duration between intervals. This is the Silverado Canyon location. The USGS gauge gave this amount of precipitation. My calculation said at that same point, it should be a little higher. Now this is composite so that it's capturing the moisture in the volume of air above the ground that goes up at 14 degree, up to 14 or so degrees. And so you can see that if weather is moving, what gets measured up in the atmosphere may not fall directly onto the ground below it, and it may be falling somewhere else. So there's an issue there that needs to be understood and recognized. But this gives us the ability to calculate intensity really precisely. So here's values that I extracted using a 5-minute increment and a 10-minute and a 15 and a 25 and a 50 or thereabouts increment, because the sweeps are not precisely 5 minutes each. It gets off a little bit. But you can see this, these threshold lines, which come from a paper by Staley, Gardner, and Keene in 2014. I might note that this is Joe, who just spoke to you. So he participated in this, but this is helping me understand and demonstrate why the 91 freeway fire may have generated the sediment that it did to close the freeway, whereas in Silverado Canyon, no debris flow was noted. And certainly none made it out to the place where people would interface with it. So that's a good use of the quantitative analysis. A brief comment about the Sepulveda Pass fire, which is another really small one located about midway between the Los Angeles and the Santa Ana radar stations. So the Santa Ana station is in the blue circles and the Los Angeles station in the red inverted triangles, and you can see they're different. And I discussed that, and this is for the December 12th fire, or rainfall event, by the way. And so you can see this difference, and I did some things that are easy to calculate to try to reconcile that, but I did draw attention to it at that time. How do you get the data? Where do you go? There's a couple of ways to get to it. This is the way that I tend to use. It's a map because I'm a visual thinker. So I'm going to use Puerto Rico as an example. So that's this step number one. You select where you want to get the data. I selected Puerto Rico. Here's what it looks like once you select that. It gives you a period of record. And I'll pause here and make a real brief comment that says, Joe mentioned that you can look historically to try to understand why a fire in the 1990s did not generate debris flows, and it may have been the intensity of the fire. Well, it may have been the intensity of the precipitation that followed the fire also. And this information goes back, in most of the US, it goes back to about 1992, I think, somewhere like that. But this one starts at 97, and then the level 3 data began in 2001. So you pick what you want. This is level 3 data over here. I picked long range composite reflectivity. And I picked the date. This happens to be the date of the landfall that Hurricane Maria made. And once you select that, then it gives a display that gives you information about the data that's in that record. Clear air is blue, there isn't any. Precipitation mode is red, that goes up here to 945. There's no maintenance mode, and there's no unknown mode, which is black. This is no data. So what does that mean? Well, 945 was when Hurricane Maria made landfall and the power went out to Puerto Rico, so that station was offline at that moment. I selected a range of time, put in my email address, ordered the data. A few minutes later, an email arrives that has a link in it to the data. I click on that link, download the data, enter it into the Weather and Climate Toolkit, and pick the last one down here to view. And that's it over here. And the final step then is to export the data. You can export them one at a time if you want, or these are scenes, if you will, or scans. I tend to grab a whole bunch of them and export them. I use shapefile and also raster file and use it in ESRI products. And with that, I will stop talking and ask Scott to request to take over the screen, and you should have it now, Scott. And I will note that we're running a little long here, folks, so I apologize for that. Are you there, Scott? Do you have it? It says are you on mute? Scott, we're not hearing you. It says you're controlling the screen, but I'm not hearing you, Scott. So. Do you need me to release it so that you can turn off your mute? Okay, here. I've stopped sharing, so go back onto audio. Come on, Scott, where are you? That's not what I wanted to do either. I apologize for this, folks.
Everyone. Okay, sorry about all that. I had to completely leave the meeting for some reason. You can still hear me, I trust.
Yeah, you need to request to take control of the screen again.
I am requesting control again.
There you go. Sorry about that.
All right, I am too. And let's see if I can actually back up these slides now. I've I should be great. All right, everyone. I apologize for that. Scott Anderson with BGC Engineering here. I'm going to try and catch up on even more time now, talking about two things: infrastructure impact and the power of social media. And with respect to infrastructure impact, there's really two things there too. You know, the GEER team goes out on a project, and we're trying to observe really two different kinds of things. What are the loadings and what are the responses? And so this woman here is standing on a bridge over the 101 freeway in Montecito last week, and the bridge is still in service, so that indicates something about a response. And you can see the debris that's in front of her there, and maybe even on top of the railing in front of her, there would be some kind of a clue about the loading. And it's those kinds of observations that we want to make. I'm going to talk through this through various types of infrastructure that would be part of basically highway-based things, and then get back into residential here in a minute with the project that Joe and Jeff and I first worked on back in 2013, the Waldo Canyon fire near Manitou Springs, Colorado. And there's a lot of good infrastructure types that can be seen here. It might be something as simple as a rock slope, and the kind of event here might be, you know, maybe you get away with a free, no cost, hydroscaling event, or maybe you cause the debris flow or flood creates some kind of a hazard that didn't exist prior, and that can be the impact there. Things as simple as fences can be observed for impacts. Here's a rockfall barrier fence that has debris piled against it. Other things that might be relevant are things like guardrails. In this picture here, it's hard to see, but there's a K-rail or a Jersey barrier, which is an impermeable barrier that's on the center line of this 4-lane highway, and then 2 lanes farther back, there's a post and beam guardrail that's, of course, a permeable barrier. And this picture also shows a culvert that could be the type of infrastructure that's impacted. Of course, one kind of first thinks of culverts as plugging, and indeed that does happen. Here's another culvert that's a kind of thing that could be observed, and this culvert has a channel that has improvements to it. You can see in the foreground, if you look off to the side, a gabion basket wall that's keeping that channel open. Culverts get bigger, they become like bridges, and this one's in downtown Manitou Spring, and the debris flood actually went through this culvert as well. But before it got to that culvert, it's a whole nother story, but this debris flood went underneath the bridge here, and it subjected these columns to a kind of loading that probably wasn't anticipated. You can see the rather high flow depth and even higher splash depth as the debris flood went around this corner here. So these are kinds of observations we can make as part of a GEER team. This is a picture, I'm slipping this one in, some of you might recognize. It's not in Colorado by Manitou Springs, it's actually in Arizona, but it's a post-wildfire debris flood down a highway, in this case with an MSE wall over the shoulder. And whether it's here or whether it's in Manitou Springs, the same sort of situation, we can have embankment erosion and retaining structure failure that comes from concentrated flows over the edge of the embankment or wall. In Arizona, this happened sort of by natural levees that maybe came from, as you can see, the way the debris deposits on the road up here. It concentrated the floods over the walls and caused washouts like that shown below. In Manitou Springs, it was a simple design detail that probably seemed easy enough at the time, a 2x6 flashing board and some asphalt curbing, but that actually controlled where these big washouts were. And maybe that's a good thing, maybe that's a bad thing, but these are the kinds of observations we want to make. Now, looking at some residences here, the ones in the upper left are indeed in Manitou Springs, smaller, older homes, both of them knocked off their foundations by this event. The one in the lower right is obviously a larger and newer home that's in the Montecito area. It's been impacted. You can see quite a bit by the cars and debris piled against it. You may not notice in the lower right corner here that this is a mud line from debris flood that went by this house. So obviously homes being impacted as well. But this picture also calls it into attention other kinds of linear infrastructure that are impacted by the debris floods and debris flows, such as power and water and other utilities. When you look at a house and a picture like this, I mean, you know, almost what else can you say, right? You know, it's really had quite an impact. But one thinks about vulnerability. You know, one of the things that's necessary to do a full risk assessment in this area is to know how vulnerable occupants are of structures. And so observations such as this and structure response are very helpful in understanding that vulnerability component. Here's another home in the Montecito area that shows a loading, not this time from boulders, or at least not in the final state, but from mud. These people up here in the upper right are nearly waist deep wading through mud to get to this home. That took a pretty hard hit on the right-hand side over here, but actually we've got dry grass and an empty patio over here, so it really acted as a debris dam, and how it responded is one of the things that we could note. So those are the kinds of impacts that we're looking for, and why is social media so intriguing and powerful, I think, in terms of capturing the loadings and the responses that come from them. And these two people in the two pictures here on the screen both have cell phones in their hands. One of them, I think the woman's probably talking on hers and the guy's holding his, but we all know that they're also there to take photographs and videos. And in this case, these two people are taking pictures, perhaps, of the aftermath of what happened. In some situations, people are actually taking pictures of what's happening. This is an advancing mud wave, and it's a still picture that I have from the Los Angeles Times here. But if I'm judging the man's elbow right in the blue jacket below us, he's taking a video of this, and half the people or more, a significant number of people like this man will want to post that information. They're citizen scientists and they're interested in sharing what they've just seen, and we'll find that stuff posted in social media sites. One interesting thing was, you know, a few years ago when I was looking at this, I found most of the interesting videos on YouTube. Last week when I checked into things, you know, I was finding a lot more professional coverage on YouTube, and I went to Facebook, and some of you, certainly my family, laughs at the idea that I'm talking about going to Facebook, but you know, I went there and found some videos that were of the quality that are interesting. Now, one thing you need to be aware of, to be good in reconnaissance, these people are recording an extreme event. That's something they haven't seen before, and some of their language is also extreme, and that comes with the territory. But this is a picture, if you haven't seen it, of a Prius floating down an advancing wave of debris flood down this street here. It's really quite something to watch this link. It's also interesting, sort of from an understanding of what's going on perspective, the people did turn out to be okay. I saw it through some other linkage later on. But this still shot that I caught of it on the right-hand side, this is the taillight of the car over here. And you can see this mud line on this garage. This street has already experienced a bigger flood than the one that this Prius decided to surf down the road. And that's interesting observation that can be used. And you know, part of the reason why this stuff is so important, I think, for debris floods and debris flows is because In an event like this, it's not that these bridges crumbled and they're going to be here for weeks or months as we pick them up and we can observe what happened. It's mud and it's debris and it gets picked up in a big hurry. This is kind of a Where's Waldo image of earth moving equipment that, you know, loaders here, loaders there, loaders over here, excavators down here in the lower right. Everybody's out there right away cleaning up what in our case is the evidence to what we can see. So going back to some pictures you saw before, I'll call this now sort of the old school reconnaissance. The truth is, when we took these pictures, we were looking at how big of a flood might have caused this, and why is this debris on the wrong side, quote unquote, the wrong side of this debris fence, and what's that little rock doing up there on top of the K-rail right there? And the answer to those questions comes in somebody's video who was parked on the highway there, unable to go any farther, and they took these images. They didn't get out, fortunately. They took these images, and you can see the rockfall fence in the background, and this is the K-rail right here, and the whole debris flood is captured between those two lines. Here's an image of somebody, a video of somebody taking that other video. They're back by that black arrow back up there. And this person is such the scientist that they're describing the pulses that are passing by and giving us real information. We could have done velocity measurements from this. We haven't done it yet, but it could be done. And this is after the fact. And that could even be the rock that we saw sitting out there on top of the K-rail when the whole thing is cleaned up. So this kind of evidence is really powerful. And if you come a week later, which is what happened when I'm standing over here pointing at this pile of debris, wondering whether it was coming from excavators digging out this channel or whether it was actually a lateral margin of a flood through here. Just 1 week after the event, you can get a sense of how this stuff changes. These are other pictures down low of this rather interesting home on Williams Canyon. But if we go to the next screen, we'll see some you know, before and or during and after photographs. I should have them in the inverse order here, I suppose. But you can see this open door and this boarded up window are right here, debris flow coming down, same sort of thing, 2 openings here and flow coming by the house. So we have real observations of what was subjected there. And finally, just the use of Twitter is an intriguing thing. Later in 2013, I worked with some folks, an organization called EPIC at the University of Colorado in Boulder, where we, with professor up there, Shide Dashti, and we looked at the use of tweets to see if we could get some information. And it takes we're fairly successful, I think, at the time. We found these 3 photographs. It took about 200,000 tweets to find these 3 photographs, but they're geo-referenced photographs of things that we hadn't seen otherwise. And I think Twitter is a much more popular platform now, or maybe not popular, but much more used platform now. And the availability to mine those information, both in search and streaming modes, is available to all of us. Oops. This is just an example of something I went to yesterday, and an online application called Social Bearing. I typed in the words debris flow, and it gave me a chart of when these things were used. It put some nice hashtag clouds and word clouds together of what people were tweeting, excuse me, and it was pretty interesting what can be done. I don't think this was available just a couple of years ago. So in conclusion, these boulders here are probably gone now. GEER is mobilizing a mission to the Montecito area. These boulders won't be visible there. They're caught by people who are there sooner, and they're posted in places where we can see them now. And so that's valuable to understand, especially perhaps if you're the designer of that modular block wall off to the left and it was subjected to a loading event that you probably hadn't considered, given the size of these boulders and the size of the trees, the woody debris that are hung up above it. So I went kind of quick there, but I want to save just a couple minutes for time, and I recognize we started a little late and I goofed it up there with somehow or other with my mute, but I'm done, and I think we'll move into a time where we can answer more of the questions that I've seen come in on the chat pod.
Okay, good. Thank you, Scott. Can you give up the control of the screen there, and I'll take control again? Okay, good. I think I've got it now. So what I had on this screen is some fires from Montana, Washington, Oregon, Nevada, and then the Nuns fire up in California, in Northern California, and then the Thomas, and I put a big exclamation point here. I actually made this diagram on the 24th of December and said that's a potential area, and it happened last Tuesday. So I won't leave that one up, but I will leave this one up and say that if you have a question and I still want to hang on for another minute or two, that we'll try to open up the chat box here. I'll see if we can, let's see if I can figure out how to do this. There's some guidance things here. How did rainfall rates compare with those predicted for Montecito? And I don't know what the rainfall rates were in terms of the historical radar data, but that will be in the GEER report when we get that done. You can see a comment about 30 millimeter per hour. And again, I'll compile the radar data and that'll be in our report. What soils database do the USGS hazard maps use? Joe, can you have a quick comment on that one?
Yeah, the soils is the debris flow likelihood model uses a variable called the K factor, which is meant to characterize erodibility for the universal soil loss equation, and that's the soil data that's used by the USGS probability model. There was another question asking if it's used just for the surface or for the whole soil, and the answer to that is that I believe it's the top meter or whatever the top increment of data they have. Sometimes they just have one value for the whole soil column. Other times they have it broken up into different depths, and in that case they will use the top most depths.
Okay. Thank you, Joe. Somebody's got to, yeah, somehow turn that down a little bit, too much echo. The next question, what is your opinion on using reflectivity data versus NOAA computed rainfall accumulation products, digital accumulation amount? That's a very good question. I intended to cover that. I thought that if I went down that path, we'd be there a long time because there's a lot of products on the NOAA radar availability. And I have a paper that compares that for OSO landslide. And I like the reflectivity data because I can calculate the intensity. It may not be the rain that hits the ground, but if you understand what goes into the calculation of the cumulative rainfall amounts, that blends in stations from the region and some other models. It's a model output as opposed to the reflectivity per se. But still, it's a valuable resource and maybe what we should be doing. And maybe we'll wind up there as a standard once we have more people trying to use this data for the purposes that we're trying. Okay, let's see. Is anyone collecting or causing to be collected high-res satellite images of Montecito? And it would be nice if they're getting some good high res. I don't know the answer to that. I have asked the question of a representative of the U.S. Geological Survey. They do have some people on the ground there and have been there since I don't know when, since over the weekend anyway. But that'll be coming, and when we find it, we'll put it into the GEER report. And there's a couple of blog sites there that have been posted. And looks like Scott made a comment about GEER using drones on many reconnaissance missions, and we do have access for one, and we may use it. I think the scale is big for what we might want. The use of LiDAR to evaluate impact areas. LiDAR is a fabulous tool. And I can think of ways that it would be very useful. It takes a lot of post-processing to get it into a usable format, and we don't. And typically, we would have to commission that in order to have it available for us. And our report will be done. That will be probably a post-GEER report finding, unless it's already available from some other source that we could use. At OSO, when we went in there, we were 2 months after. the event occurred because of the search and recovery aspects of it, and the state of Washington had produced all of that, and it was available for us, and it was a fabulous resource. Another comment, Joe, was that you?
Yeah, I was just going to chime in on the use of LiDAR. The USGS has done some pre and post debris flow LiDAR work in some of the burned areas in Southern California. So they've been able to pinpoint some of the source zones for erosion and deposition within the watershed. And then also from Irene's question about debris flows being a one-time event, it depends. Oftentimes the hazard will continue for 2 to 5 years until the soils begin to, or the vegetation begins to reestablish in the burned area. And then even up to 10 or 15 years, you can still have high fine sediment yields from a burned area. So it takes a long time for the hydrology of the watershed to get back to where it was before the fire. But the debris flow event, yes, there is a continued hazard of debris flows. And I know that for Montecito, they have more rainfall predicted for this weekend. So it'll be something for the people in that area to be cautious of the possibility of more debris flows.
Yeah, that's true. And I think we probably should wind down here, but I will comment that my experience with debris flows from other states, primarily Utah, is that once the canyon is cleaned, it takes a while before the rock formations develop a colluvial mantle and alluvium in the bottom of the valley that will allow another big discharge of sediment like what occurred in Montecito. So the next event that comes may be enhanced water flow or sediment-laden water, but not debris flow. Those boulders that came down are not up there to come down again. I don't know if others are up there. That's the kind of thing we will be looking for. And I think the USGS is currently looking at that as a future immediate hazard. So with that, I'll say thank you to everybody. And this will be posted. You can get a link to it from the GEERassociation.org website. And if and let me switch to this final, I got to go back here. This final slide has our email addresses. So if you'd like to communicate with us, and the email addresses were not in the invitation to this webinar, feel free to do that. Our email addresses are all listed right there. So thank you all very much. I appreciate your participation, and I hope you enjoyed the presentation as well.